done for the people, for the citizens. Everyone uses navigation nowadays, satellite navigation. We are close to also to absorb soon the data from the Earth observation and use them on our phones, tablets, and so on quite regularly. There is another new program of space agency, all space agencies, which is space situational awareness, which covers 3 areas: space weather, space debris, all these small things that are flying on the, especially on the low Earth orbits. And the third issue is near Earth asteroids, the danger of them, but also a kind of a benefit we could have from them, concerning that they are very rich in a very precious metals, for instance. Then we have technology and exploration and space science, and this is more or less the focused area of our activity. We don't do rockets, as you see, or launchers. We don't do human or man space flight. We don't do a bit of, too much of telecommunication, but perhaps in this case, it will change it. So realization of the program, we are very quick in access to ESA. It was the shortest negotiation in the history of the agency, and after a year and a half, we are still in the learning phase. So we try to understand how ESA is working, and it's not easy because this is like a club. ESA is there are written rules and there are unwritten rules, and to learn what are unwritten rules takes time. The Polish Space Agency already told you that this is quite well advanced legislatively and accepted already by the government, so it should be okay. We were lucky in getting in three areas some hints of how space is important. 3 areas of strategic research and development plan for Poland, so technology, environment, and security. We have a Copernicus implementation plan ready, and what is a big surprise for everyone, we have perhaps the biggest numbers of enterprises and institutes registered in Europe, registered in ESA. After a year and a half, we have more units in this ESA circle than Italy, for instance, which is, of course, on one hand is promising, on the other hand it's perhaps, a bit, let's say, going too much, because it's difficult to find the money to feed 140 units. Then something on the side of the national program, although this is not called the national program because this is financed also by the Minister, mainly by the Minister of Defense. We have now a feasibility study for 2 dual-use satellites, Earth observation satellites, and this feasibility study was launched recently, and if it's successful, we will have to build together with some foreign partner 2 quite advanced satellites in 4-6 years. Now about the institute, we were founded established in 1977. We have 3 branches. The main one is in Warsaw. We have also solar physics branch in Wrocław and astrogeodynamics, which is very close to what you do here with the laser station, ranging station with Borowiec. We built in 60, now it's about 70 space instruments. We have close now to 200 people, and as you see, there are more engineers than scientists, which is perhaps the result of a big interest of young people in this area, in engineering especially, not that much in science. The main fields of activity is space physics, spatial geodesy, remote sensing technology, and I will give you a short overview of what we do in each of these branches. And of course, we support very much our government in shaping the national space policy. So how the institute is organized, we have six research units: so solar physics, solar system dynamics and planetology, solar system physics and astrophysics. This is mostly interplanetary medium, or interstellar even, but close interstellar medium. Then we have plasma physics group, planetary geodesy, and recently established, like 5-6 years ago, Earth observation group. including not GMES, but Copernicus group. And we have 4 labs. This is important because we can build our own instruments for space missions. And they are, let's say, looking into the areas. One is mechanical, another is optical, the 2 are electronics. So this already, so our main goal, of course, is to participate in the space missions, and these are the examples to the left. On the left, you have this 4 cylinders. Is a very small sensor. We started cooperation with which we started cooperation with ESA, but not directly, because at that time it was 1990. We were not even let's say associated. We had no agreement with ESA. It's just that we had colleagues, and in this case it was University of Kent and Canterbury, John Jarnecki, and they invited us to build a small sensors for Huygens, for the Huygens Prof. There's a surface science package, and inside this surface science package we were asked to build this 4 temperature and thermal conductivity sensors with a very simple principle of operation. Inside these cylinders on the axis there is a platinum, very thin platinum wire, and of course platinum is a very good, very well calibrated metal to measure temperature, as the resistivity changes with the temperature. So if you measure resistivity, you measure the temperature, and also if you heat a bit the wire, then you get the let's say the heating rate tells you something about the thermal conductivity of the medium. So these 2 big ones were foreseen to work in the hypothetical ocean on Titan. Titan is a very strange planet or satellite of the planet, but it's the size of a planet because it's very cold, but there is a liquid on the surface in 100 Kelvins. And this liquid, of course, is not water, but this is a mixture of ethane, liquid ethane, and methane. And it's it was very tricky to deduce it without seeing it, because Titan is covered by dust and clouds, so not much is seen from the Earth. But the people somehow figured out that it should be liquid, and we prepared these 2 big cylinders for the liquid, and the 2 small ones were for the atmosphere descent. Unfortunately, it happened that the hypothesis was true, but there was no global ocean, so there was a local lakes or rivers, and we didn't land on the rivers. So what we measured was just the temperature profile of the atmosphere and thermal conductivity of nitrogen, which is not very fascinating. But anyway, all this sensor worked also after landing, so it was a good technology demonstration. And this one, what you see here is two other pictures. This is our biggest achievement in engineering. This is the MUPUS experiment for the Rosetta mission. We are not the leading party here, because this is the German experiment, DLR, the German Space Agency Institute in Berlin now. But we built on, let's say, partly from the Polish funds, partly from the contract from Germany. We built everything what you see here, also the sensors. So it was in 1995 when it started, and we learned a lot how to, not only how to cooperate with ESA, but how to build a very advanced instrumentation. So here you have a list what we are involved in. So a lot of space projects. Bright are small satellites. Polish contribution to the Bright constellation. Pepi Colombo is the mission, ESA mission to Mercury. Herschel, this is the microwave telescope that stopped to operate like a year ago, but brought a lot of interesting results. Relek is a Russian space agency mission, magnetospheric mission. Obstanovka is something on the International Space Station, I will tell you later, and ACE in the same. Taranis is the French mission to study the magnetosphere. IBEX is the American mission to investigate the local interstellar medium. And Rosetta, I told you about Coronas Photon, Russian mission to study the sun. Phobos Grund mission to Phobos unfortunately failed. Mars Express and Venus Express. I'm sure you heard about the missions to orbiters to somehow monitor what's going on the surface of these planets. We do also, of course, data acquisition. Having this observatory in Borowiec, we have the reference station for GPS in Borowiec. We have laser ranging station in Borowiec. We have an EGNOS station in Warsaw, and a number of labs doing astrodynamics in 2 big locations in Poland. Of course, we do a lot of interpretation and modeling. We do applications, and we do data exploration and dissemination. But of course, something that we are quite unique in Poland, because there are other institutes in Poland that do it also, but space technology development is our let's say own homemade invention. So no one is doing this in Poland apart from us. So you can see here on the left, to the left, this laser. Sorry, thank you. So laser station. This is something that was prepared for Pobosgum. Sample taking mechanism. I will tell you. This is bright satellite. Again, this sample taking mechanism. This is some satellite image that we use. This is the EGNOS station. So now about the departments. The solar physics department is now about 20 persons, and they are in a very fortunate position, because they worked for a long time, cooperated with Russian colleagues. So they were on many Russian missions at the time when Europe didn't do too much on the sun. And now, when the solar orbiter was launched, this group was very, very much welcome and appreciated because of this long history of successful experiments with Russians. And since they also have a good cooperation with Americans, there is a possibility that they will be with these experiments on 3 different missions, because there is something on in parallel to the solar orbiter. There is a Russian mission called Interheliosonde, and there is a Solar Probe Plus American mission recently accepted. And just to show you the history, this is the first space instrument, Polish instrument, that was set to space by the vertical rocket in 1970. So already almost 45 years, very, as you see, very old fabrication technology, but worked. And the principle of operation, which is here, you see the black crystal, is still kept by this group as their, let's say, intellectual property, and they developed to very sophisticated now devices like this one, a very small one. That was on the Styx mission, on the Sphinx mission, the Sphinx experiment on the Russian mission, on Coronas, and just to show you how good they are in obtaining the spectra of the this works in as you see in X-rays. So these are the spectra that usually you get from flares, solar flares. And the black one is GOES spectrum from a very good American mission that is working, generation by generation has been working for already 30 years. And the blue ones are these peaked ones. These are very good spectral resolution, are the spectra obtained from this instrument. So, and they are perfectly calibrated. So now they are a reference for almost all solar physicists. What is the absolute abundance of elements of ions in the solar corona, in the solar photosphere. Now, plasma physics department is a big one. Again, one of our flagships concerning the instruments. So they do Earth ionosphere, magnetosphere, but also fundamental plasma physics, and they use radio spectrometers as a let's say, tool for measuring the properties of plasma waves. And this is one of them again, this was on the Russian Compass mission. It didn't work too long because the mission, I think, didn't work too long, that we use as a heritage to go for instance, for this mission. This is International Space Station, and here you have a place where the Abstanovka experiment is located. And we delivered, first of all, electronics to measure, let's say, the influence of the station on the plasma flow around it. So how the plasma changes with having such a obstacle in front of it. And we also developed two antennas, 3D, let's say, so in 3 directions, electric and magnetic, for this experiment. Now, plasma physics and astrophysics, this is mostly theory, although we participate in the IBEX mission, NASA mission, which was very successful, this is medium class or small class mission, so not too big, only two instruments, and measuring something very exotic, namely neutral atoms, which are very difficult to measure because they don't interact easily. So first we need to ionize them and to find the let's say the detector to detect ions, which is already easier, and of course to know how to calibrate everything. And the story about it is that we are, of course, here, somewhere here. This is our solar system. Here is the sun, and from the sun, the solar wind is blowing. And on the other hand, from the other side, you have an interstellar wind. So they collide, and we at that moment when this picture was made, it was not certain what are the properties. So what is the magnetic field in that interstellar? What is the speed? What is the density? So no one knows, is it the bow shock in front? Is it magneto supersonic flow or not? But at the time it was assumed that it is. So there is a bow shock, there is let's say a boundary when these two flows, let's say, do not penetrate from one side to another, which is called heliopause, and there is, of course, this inner shock, which was observed by Voyager already. Yeah, so a lot of interesting physics here, involvement of cosmic rays, neutral atoms coming from here. And of course, neutral atoms are not deflected as ions. They just come to the inner solar system. Hydrogen is mostly ionized by Lyman alpha, or excited by Lyman alpha, and helium atoms, on the other hand, they are usually not too much ionized. So helium, neon are well observed, but you need a very, let's say, good sensitivity of the instrument to observe them. So there was a mission that started this investigation. It was Ulysses, the mission that was for the first time flown over the solar poles. And there was an experiment, the German experiment, neutral gas, called neutral gas or neutral gas in German. And it was the first successful measurement. Here you see the signature of these helium atoms. Hydrogen was not able to be measured because of the low sensitivity of the detector for hydrogen, but helium was very well measured. And it was the first time when the parameters of the interstellar medium was very precisely, I would say, determined. So then it was Ulysses was 1990, so it was a long story. But then came IBEX in 2008, and it measured, of course, it measured helium by quite different technique, and there are still debates how to combine the measurements of Ulysses with those of IBEX, because there are some differences in this parameter. But the people are now coming to the common conclusion, so it's going in the right direction. But what IBEX was really doing, I mean, as a what he measured was considered as a discovery, even by NASA and by Americans, was to observe these ribbons. So these are, as you see, energetic atoms. Usually these helium atoms are up to 100 AeV. Neon and oxygen is 0.5 keV, but here we have atoms tens of keVs. So it was strange to observe such neutral atoms of such energy, and the explanation is that they are somehow, let's say, recharged, or ions are recharged. They interact here on these boundaries and produce such a ribbon. So one of the explanation of the ribbon, not currently, let's say, considered as a valid one, but still the first coherent was provided by the guys from our institute. It was the hypothesis that this ribbon comes from the region here. So Sun is here. We are in the local interstellar medium, but a bit outside of this local interstellar medium, there is a local bubble. So on the interaction region between this local interstellar medium and the bubble, something happens, and the neutral atoms could be generated to produce a ribbon. Now we have a small bodies dynamics and planetology group. This is a group that historically dealt with dynamics of comets and asteroids. But from some time we also do planetary atmosphere and surfaces. And then, of course, in the context of the ESA, mostly ESA planetary missions, so Cassini-Huygens, Rosetta, but also Mars Express, Venus Express, and Herschel, that although it was mostly dedicated to measure galaxies or clusters of galaxies, but also did a bit on planetary science, observing planetary atmospheres. But here what I wanted to show is something that came from this dynamical investigation. Namely, you can somehow produce a model. Usually, this is a comet. And the comets are specific in the sense that they don't produce the material or volatiles. They sublimate from the surface, but not uniformly. There are active regions, and there are, let's say, regions covered by dust that nothing happens. So if you have let's say, active regions, you can somehow assume there is the area of this region, the position of this region, and then, of course, there is a jet force, very, very small, but still significant. It changes the orbit. So, analyzing the orbit by orbit, let's say, several apparitions of a comet, how from the just positional information, you can try to deduce, to retrieve the parameters of these active regions, and this is done in our institute. No one believed that it is true, but recently it happened that they are sometimes very close to really good prediction, because now the comets are also the cometary nuclei are also observed by telescopes. You can see where this activity comes from. And another, again, the something that is connected with dynamics. You have heard about this famous asteroid that was discovered in 2004 that was supposed to hit the Earth in 2020 something. And our group, which is very good in doing this kind of calculations, they somehow found out that 2029 is not true, but 2036 is more probable. And they even found the locations of the potential impact points, which, as you see, is not in our zone. So we are, from this perspective, we are secure. Yes. But this, of course, this is a probability only. This is not certain, because it's very difficult to prognose in such a long term. Planetary geodesy. Again, I think that they meant on the theoretical side, they made field is polar motion. So they use very advanced mathematical tools to deduce the polar motion, also predict the polar motion from the observations. There are a lot of different kinds of observations, but somehow they are here in the front of this investigation in the West. Also they do satellite orbits and navigation, but perhaps the most important is that we have all this instrumentation. So two reference stations for GPS, EGNOS, and of course this laser ranging. And we have something very strange. I will not tell you too much about it. These are two very long pipes, and they located in the cellars of a very old castle in the Sudety Mountains, so very stable environment from all point of view. And looking how the water table in these pipes changes, you can deduce what's going on in the range of frequencies that is not covered by the seismometers. What's going on with the tides. So they observe, for instance, the tides from the North Sea being like 700,000 or 800,000 kilometers away from the North Sea. So very, very precise instrument, but very strange. Also, this is the laser station that we have in Borowicz. And this is something again. And this is something that again is specialty of the institute, namely this small thing. We are very good so we have a, let's say we support the Polish atomic clock scale, time scale, having a number of atomic clocks and also rubidium and cesium clocks, and having this expertise, the people there, they developed something that is called time transfer system, and it is used by all the time lapse in the world to somehow exchange the information, to synchronize, in fact, the atomic clocks around the world. Earth observation group is a new one, so the main area of investigation is very high resolution data processing. Very high resolution is about 1 meter resolution. And here we develop, we don't do operational processing, we develop methodology for this processing, and mostly it concerns the classification of the images, automatic classification and automatic land cover change detection. But we do a bit also on border security and climatology in the context, border security in the context of European FP7 project, climatology, because we just got a number of two at the moment specialists on that, and they are developing this area in Poland. And now perhaps the most important from the point of view of what is unique in the institutes are these engineering labs. We have quite a lot accumulated, quite a lot of experience in this, because we have still specialists that started 35 years ago with the beginning of the institute, and so they are really good experts on building instruments. And here you have some examples. So this is a very sophisticated block of electronics for Herschel. Again, this is for Herschel, and this is the Herschel itself. So this was something that controlled one of this hi-fi instruments. This is again very unique instrument. This was done by a big international consortium, but what we got from it was to deliver, to develop and to provide control units for all these experiments. So a lot of trust was put on us, and we somehow managed to do it. Although it happened that in the first month, after the first month of Herschel operation, this block failed. It was switched on, the instrument was switched on for half a year. There was analysis what happened. Fortunately, it had a redundant block, so the issue was just not to damage the redundant block. So the analysis was just done for being sure that nothing happens with the redundant block. And the analysis shown what was the problem. It was not entirely our fault. It was somehow on the interface, as usual, with the other instrument, with the other unit. And fortunately, after having the reprogramming, it was switched off, this redundant block, and it worked perfectly for the next 3 years. So we were lucky. And this is again something that usually the failures in space are more interesting than the success stories. Here is the failure again, because of this instrument, the Phobos ground. This is the penetrator that we developed, this part, for the Phobos ground. So we were approached by the Russian colleagues a year and a half before starting, before the launch of the mission, that they somehow are not sure if they will be able to take the sample, since they assume that there is a sand-like material on the surface, but then they come to the conclusion that it could be rock. So what's going on if it's a rock? And they ask us to develop something to take the sample from the rock. And we repeated the development from Rosetta, but changed a lot. And here is something that takes sample on the end. Here is a hammer that just hammering the thing to the regolith. Here is the scanner for the Mars Express. Interesting story. And now, just to change a bit this let's say list of what we did, it's just a general philosophy. We have like 2 different approaches to building the instruments. So first thing is to build the instruments according to the highest standards, so ESA, NASA, and whatever. And then of course it takes time. You build a lot of, you have a number of models that you have to build to pass all these reviews in ESA. So usually we have to build like 5 to 7 models. Each one is more advanced than the, until we can do the flight model and flight spare model. And of course, this requires experienced staff, a lot of time, reporting, and so on. So usually this is let's say a job for a good group and a group that has a number of I don't know, 5 to 7 specialists that each one is expert in something. And of course, all these steps have to be very carefully done. At each step you have a test, you have certification from ESA, and so on. So sometimes it's not a good way, because then you have to plan like 5 or 7 years in advance. And the customers usually, if it's not a big scale mission, they are not ready to wait so long. So they want something simpler. So we learned how to do something simpler. This is the philosophy that also was implemented by SSTL, the Science Space Technology Lab. So to do the things that are perhaps not 100% space qualified, but if you have a good specialist and they have a good intuition, they can make the things simpler, not really risking too much on reliability. So this also we somehow master how to do it, and this is especially interesting in the context that if someone is now, a new customer is coming to ask you to do something, then you cannot tell him, well, wait 7 years, give us 100 million euro, and then we will build it, because it's not the market case. So this is perhaps the better approach to build something quickly, but still something that will work. So now I did something. So now we are here. So now again the practical cases, and this is the first this something that we call mechanism space, and this is not only what we did for Rosetta or for Phobos, but many different things. First of all, coordinate systems. This is the example from Rosetta. You know, to dip into the comet, because this was a cometary mission, and this is just a cometary penetrator. Usually you have to be a bit farther than just 10 centimeters from the lander, because first thing is that if you start to dig very close, you can somehow make some mechanical perturbation on the lander. Another thing is that if you want to make a thermal measurements, and this here you have temperature sensor inside this penetrator, you need not to be perturbed by the lander in terms of shadow, influence on the thermal properties and so on. So the best thing is to be 1 meter away, and to get this penetrator 1 meter away, our engineers invented something very clever. Namely, they used a pair of tubular booms. So just the metal tapes that are spooled, and then if you just use the motor to wing to move the spool, this tapes, then from the flat they have some memory, so they form a cylinder, and this cylinder is much more stable mechanically than the flat tape. But there is one problem, namely you see where the center of gravity is. So it is much higher than the tapes. So you have instability normally on the Earth in the gravity. You have instability in torsion of this pair. Fortunately, we are working in the microgravity environment. On the comet there is almost no gravity, so this is not a problem. And this was a very good observation by our engineers, because usually when you have a Earth oriented approach to engineering, you will never invent something like this for the comet. So this was one line of development. Another is something that we use now very successfully, is to use not the hammers like this. Here is a hammer that is hammering this device, but then of course you have a limit. You cannot hammer this head here to the ground. You can hammer only this rod. So the limitation is the length of the rod. But if you have something that has a hammer inside and electronics inside and motor inside, like the mole, then you can penetrate down to several meters. And this is the recent case, because it happened that there is a mission, NASA mission called InSight, and the idea is to set a observing station on Mars with the seismometer, this probe, thermal probe to measure the heat flux on Mars, and meteorological suite of instruments. And the Germans that were called from DLR, that were responsible for this mole, they had their own device inherited from some Russian experiments. They were not able to go deeper than 1 meter and 80 centimeters, and the requirement was to go 5 meters below. And the problem was that the hammering mechanism failed. So they were not able to hammer, because at some moment the hammer was so already damaged or whatever that it didn't work. So they asked us in October to build something for InSight, because InSight is going to, the flight unit is due to, I think, in July. So we got 7 months to develop something like that. And after 3 months, we developed something. We just improved the German, let's say, construction. But after 3 months, we were able to penetrate 5 meters without any problems. So now it's accepted, and we are just delivering the 5 flight units for this. So this is the result of the experience we gained mostly with Rosetta. And here is something that is again looks very strange, but it was once ordered by the I think by the European one of the European partners. For instance, if you want to have a seismometer on the planet, again you need to somehow locate it quite away from the lander, because it's a very sensitive instrument. So for that you need some means of transportation, and this is ultralight manipulator. So manipulator is lighter than perhaps the load here. Again, it is based on this principle of tubular booms, but in this design it's 3 degrees of freedom. So it can rotate, it can be inclined, but also can be extended. And we do also, so this is one. We do also a lot of testing. So as you know, in space, the most important thing from the mechanical point of view is to get a, let's say, a reliable contact between different kinds of materials. So usually you contact plastics with metals because then they don't cold weld. They don't get cold welded. And for that you need to know all the friction properties of this, and we developed special instruments called tribometer to measure this, which is also used in a number of ESA projects. Now this is Cassini and this is Rosetta. So these are the sensors of Rosetta. You have seen this thin rod, and inside the rod there are 16 temperature and thermal conductivity sensors evaporated on the magnetospattered on the Kapton foil, and they are usually, you do it with platinum, but platinum was too expensive at that moment, because with magnetospattering you get 1% efficiency of spattering. So imagine that you have 2 kilograms of platinum and you get 1% of it spattered, the rest is lost. So it was not possible. We did it from titanium, but it works. Then plasma space mission, we do radio spectrometers. Here you have see this antenna for Abstanovka. Again, a clever mechanical design because it's folded. Should be 3 orthogonal rods, but in the folded configuration and transportation, this is just like 3 parallel lines. So there is a clever way of making them, let's say, deployed. Then something that we do for planets is spectrometry. So this is the Mars Express design, and we contributed with the scanner and with the electronic power supply system. But at the moment we are able also to do our own planetary Fourier spectrometer, so we can reproduce all this chain of units also in our lab. So if someone wants to get a PFS, we can do it. This is something for Bepi Colombo. So this is again a scanner. Bepi Colombo is a mission to Mercury, and of course the most important thing is from the orbiter is to see what is the mineralogical, let's say, composition of the planet. And for that you need a very good spectrometer. So spectrometer is delivered by Germans, but we contribute with the scanner mechanism that can change let's say the position of the field of view with using some mirror, and then you don't need to rotate the satellite, you just rotate the mirror and get the instrument looking in the right direction. And of course, we are also interested in interpreting data. We have a number of geologists in the institute that can do the interpretation of this mineral spectrum. This is this line of X-ray observation of the sun, and this is sticks for the solar orbiter, a very complicated instrument that is with the PIs from Switzerland, but we do quite a lot on thermal design, on detectors, and also on electronics and GSE. And of course, we are expert here with interpretation of the data, again the heritage from these old times. These are the special electronic blocks. So one is for integral gamma rays. So this is anti-coincidence block, and this is the Herschel. This already was shown. So just the how it looks inside. So there is a lot of boards, electronic boards with a lot of elements. All together there are 16 kilograms. You see more than 130 signals and so on. So very complicated thing, and really the key element of the whole instrument. So we do a lot of DC-DC converters. Arnold's mentioned that we can go, let's say, to the market. If someone will ask for a company to build DC-DC converter, we can definitely recommend that SRC or a company around SRC can do it. So this I will speak now the satellite. So this is a very small but very efficient satellite. It is 20 by 20 by 20 centimeters, so a cube which is like 8 CubeSats, and it carries only one instrument, which is a camera. And camera is not observing the Earth, in this case it's observing the stars. What is the idea behind it? That if you have a constellation, in this case of 6 such satellites, and they are just dedicated to observe very bright stars, you can continuously for 3 years observe a number of bright stars with a very good integration time. So you can really detect very small changes in the photon flux, in the light from the stars, and from that you can deduce. Usually this small variation comes from the oscillation of the star, and this let's say the science behind it, which is called astroseismology, is ready to produce internal models of the stars, observing the modes of the excitation of these stars. And so if you observe a number of stars for a long time, in this case 3 satellites observed in blue, 3 satellites observed in red, then comparing this, analyzing this long time series of the spectra and in 2 spectral ranges, you can get a lot of information about the excitation and finally about the internal structure of the star. So the consortium is composed by, let's say, there are 3 countries involved: Canada, the owners of the let's say of the design, SFL from Toronto, Austria, and Poland. And each one provides 2 satellites. So one of these satellites is already flying, and another one will be launched in a month, in July. Then something again that perhaps will be of interest for you, then we developed something to observe something optical. So these are cameras. I think this is 20 centimeter diameter, to observe radiation coming from gamma bursts. So if you have if you excite by gamma the particles in the atoms in the atmosphere, they just emit the light, and then so you need something that is wide angle and observes all the time, and doesn't need to be very complicated, but of course somehow also is able to change the looking direction. And this design here is called Pie of the Sky. And so these optical flashes from gamma ray burst was observed very successfully. They were very lucky just after installing the first one a month ago. Later there came a big gamma ray burst, and they were one of the first to observe it. So very successful. And there are several locations of this instrument. This can also be used, and we analyze it for observing space debris, but there is not too good accuracy, so you need to make this telescope a bit bigger. But since they have a very good electronics, so CCDs that record everything and archive everything, you can do this analysis ex post, and definitely we see some traces of space debris, although big chunks, it's not the small ones, that are in this recorded archival images. Of course, having such a wide range of activities, we have a lot of international cooperation, and I would be very happy to cooperate with you. It's such a good institute, so there are already plans. We are thinking about this laser station, so there is a lot of potential in cooperating. I told you about Bright, but just to tell you how many people were involved, these are 25 people that at different stages. Not that all of them worked all the time on Bright, because of course this is a small satellite, doesn't need it. But you have a lot of specialists from different areas that finally are able to produce the final device. So you need also to find a launcher, to negotiate and so on. So you have people, you have engineers here, managers, and also the people that can do all this stuff, organizational stuff. Earth observations, we have, let's say, we participated in a number of projects I mentioned, but what is perhaps important, that we proved that this Earth observation, let's say, programs can be very useful. And here is an example. This is the image taken from the radar satellite, I think, or somehow composed from the radar satellite images. Flooding in Poland in 2010. We had a big flooding, and this is an area of, I don't know, 30,000 square kilometers, flooded by the Vistula River. And of course, at that time, the main concern of the fire brigades was how much water is in all these places, how soon it will be removed, and so on. So we developed a special tool for that. So using geological data, hydrological data, we were able to somehow to tell them where to look for the best places to pump out the water, for instance, from the so to speed up the process of removing the water from the flooding areas. Then another mission that we are very much involved in was Geoland, and this is an example of automatic change detection. So here is a Warsaw, water in Warsaw. This is the image from 2002, and you see fields here, and here is image from 2008. These Iconos images, already a lot of, let's say, buildings being constructed here, and automatically all of them were recognized as airports. So this was very useful, because usually you reduce them by automatic detection, you reduce the amount of manual work, which is, of course, the most costly element of all the process. Another example, I will skip it. Then, of course, we do a lot of somehow promoting this Copernicus Engineers project. And the first thing for doing this was to make an inventory of what is done in Poland in the EO sector. So if you would like to find a partner in Poland for Earth observation, we are a good contact point, because we have all this data somehow collected in this project. Already somehow this one was finished, but there is another one, a continuation of it. So of course we had to participate in a number of projects. If you start a new group, you need to find financing, and the financing for the Earth observation group came mostly from the 7 framework program projects. But now the group is quite well established. They already are able to find new projects, and I think that they are on a good way to be well established in the European research area. Here, usually you need to show that you publish, and we always do the statistics. This is 2010. Now we are moving, because as you see, we were stuck on the level of 50 publication. The yellow one are the best journals. So with the you know, Philadelphia, JCR journals, and the red ones are other. And what I need to stress is that, of course, to have a specialist, especially in such a niche areas as space, you need to educate them. We are not allowed we are not universities, so we are not allowed to give the degrees of the, you know, of master degree or bachelor degree. What we can do is to, and we do, is to carry out the PhD studies, and we have a number of specialization. In some of them we can promote these people. In technology, we take the PhD students, but we promote them at the technical university, because we have the rights to give the promotion satellite geophysics, not in technology, but soon it will change. We are fighting now for having in Poland a new discipline which is called space engineering, perhaps aviation and space, or aerospace engineering, whatever. Anyway, we are close to be successful, and then, you know, the space could be, space technology could be taught at the technical university, which would be very good for the Polish industry. And of course, what is important, you see a young pupil, perhaps 10 years old, contemplating the bright model at some of the science picnic or festival of science. So this is the future of space science, and of course we are very dedicated to somehow convince these young people that there is a career in space science and space technology. So that is. Thank you very much.
Thank you. Great story about Polish success. Okay, questions, colleagues, please. I am very general question. Seems it's a sense to think about Horizon 2020 and about this tool or options with the research councils and future and emerging technologies. You mentioned already, and I noticed from several other cases, there's this space and asteroid geology is really future and emerging technology. Possibly somebody can raise such proposals.
I think that already there are consortia in Europe, so we need to, you know, it's a good point, because we need to be quick. But, you know, the whole American program was once changed from, you know, the Americans, they were somehow considering where to go, to Mars or to asteroids. And now one of the objectives is to go to asteroids, because first of all, you have all these rare earth elements, very relatively easily accessed. Well, they are in the whole body of the asteroids, platinum metal. The concentration are 100,000 times bigger than in the crust on the Earth, because the asteroid is uniform. All these elements are in the Earth are mostly in the core. It's very difficult to dig them out of the core. So this is one reason. Another is this asteroid, this danger of asteroids. So there are two lines. One is how to somehow put something on the asteroid to make to detour its orbit, to change the orbit. Another is how to dig and how to bring the material to the Earth. So this is, you know, a long-term project. I think in 20 or 30 years, but we need to start now. And already there are consortia in Europe.
These two programs are dedicated for that. It's something 50-50 chance to be successful. And my understanding, not being very deep in field, is that besides direct technological development, say building rockets to fly to this asteroid, there's a lot of paperwork, theoretical.
Yes.
Some teams can do this work. Like in comparison, we have succeeded with European Research Council grant for quantum computing. And this colleague, his name was colleague Andy Samrines, his task is to see what will happen with the society if suddenly content computers will be built. It's the same would be in this case what will happen with Earth when we succeed with this asteroid geology.
Well, I think that there
We
is.
need to think about
No, we can even try to find it.
some leader who can rise such project.
There are European industry that is very much interested in this.
Yeah, developer.
Yeah, so you entered ESA very quickly, you said, and I am curious, what was the political strategy that you used to convince the political bodies that this was a good thing for Poland?
Well, the first thing was to somehow, tell the people that space is not science, not only science. So this was I would say this was, yeah,
Okay.
because the opinion was, we are a poor country, why we should spend the billion of euros or whatever, zlotys, for science? Because the opinion was space is science, which is not true. Space is, 7% of space expenses goes for science, or even less in terms of, let's say, the 7% goes for missions, but even less goes for the people working in science. So to convince the politicians, first thing was to tell them space is useful, and it's useful in Earth observation, in navigation, and you can benefit from it as a politician as well, because you can convince your voter, the people who vote for you that okay, we do something useful. We don't, of course, we don't build roads, because this is the main concept. But we do something that you can use. You can have a navigation system for the roads. Once you build it, you can have for instance, this system for warning in case of flooding, which is already somehow you can calculate how much it benefits. So this was the first impulse. The second was to convince that there is because after saying that there is something more than the science, you need to show who is this part, and the industry, of course, is then called. And we did a lot of work to identify industrial partners, to convince them that they can go for space, and we are more than successful, having all these 140 units. Recently, we perhaps I missed this, but recently we organized a space cluster, and the colleagues here, Sander is a president of one of the companies that joined the Polish space cluster, and this is already aiming at getting some funds from the structural money, so something real. There is an association of Polish employees, space employees also. So there is a lot of activity going on in Poland, and the third, first, not only science, the second industry, the third, the young people have a chance to do something ambitious. This is the third issue. That there is a competition for Mars rover in the States.
Right.
And usually 30% of teams comes from Poland, which is strange.
Yeah.
So we have now like 7 competing technical universities in Poland to go to this competition in the States. So the young people, they want to do something, that is not, let's say, routine, standard. They want to go for something bigger, and they have a chance.
Okay. Thank you.
Mike, thank you very much for a very refreshing presentation. And this is a tremendous sort of showcase of Poland's progress towards really being a global competitor and a player in space technology. And Bright is an excellent example. And I've been following this quite closely lately. Perhaps for Bright 2 or Bright 3, do you envisage the next generation of Polish satellites having a collaborative approach with her partners, her neighbours, like Latvia and Estonia and Lithuania and Finland? Will there be a collaboration and will there be a regional approach to Poland's satellites going into the future?
We are not too much, let's say, in front of the. So it's not very. of course, when the right was proposed, not to us, but generally, so there was a lot of objection raised in Poland. Well, can we do it? We never built the satellite, so on. So it was our role to convince, although we were also not sure completely, 100% that we would be able, but we did. And this is, you know, the lesson for anyone, because you know, when you do such a project, you don't need to have enormous knowledge. You just need to have a number, let's say 5, 6 senior engineers that can do it.
Enthusiastic.
And then, yeah, a lot of enthusiasm, and then you will do it, and some guidance. And we can, at the moment, we can provide a bit of guidance, and of course, usually the problem is that with the regional, let's say, approach to this, that each country has a specialist in, should have a specialist in different fields. So we can be, you know, like you know, this gluing part that we are just do some things that no one is going to do because there is no expertise. So this is a good approach, I think.
It's a really good demonstration of confidence building. I mean, the whole region's only been involved in space for more than 50 years. So
Yeah,
it's going back to history and really capturing the heritage of the region. And it's a good
you
demonstration.
know, Latvia was one of the leading parts of the Intercosmos program, although then as a part of the Soviet Union, but we had a lot of expertise there. The same, we are less advanced than at that time, but we had this, you know, this a good, let's say, good luck to immediately join to ESA.
Yeah. You're welcome. Yeah.
Oh, so then, immediately after 1991, would you say that you had more internal Polish funds to build this capacity, or did you have equal or more European funds? Because it seems like there's a tremendous, you know, building that took place in the last 20 years.
So I would say, just to be, you know, very, or as much precise as I can. So the infrastructure we own is not, you know, it's not tremendously. It's like 20 million euro perhaps, you know. So this is not. But this was accumulated over 15 years, so it's not an enormous expense in one year. Then the funds we got, we are not very, let's say, fortunate in raising funds from the Polish Ministry of Science, because science is a conservative area, so they usually support astrophysicists, geophysicists, because these are well established. Space is a new thing. So our financing is quite modest, I would say. So we need to, then to develop, we need to look for funds elsewhere, not from the statutory. So we now at the moment we have 20%, 25% from the statutory funds. So the government pays as well. The rest we get from the market. So competition on there are two funding agencies in Poland, one for fundamental science, another for the application. So we do a lot of proposals. There are ESA, and before ESA there was the Specs projects we applied. There is Horizon FP7 and Horizon 2020 now, and there are contracts with different parties. So altogether, you know, we get 80, but this is not a good way, I would say. You know, the proportion is wrong. So 20 to 80, you don't have any strategy in it. You just get the project. We have currently 100 projects. You know, 200 people, 100 projects. But then, you know, what is your focus? There's no focus. So 50-50 is the right proportion.
Finland is saying that 50-50 is close to danger threshold.
Yeah.
We need to be more
on the
50 on the side of stable financing.
Yeah.
Yes. People
this
feel
is
stable.
yeah. I observe how the French and German institutes, they are, you know, well established and they have a lot of experience in that. So they are, as Arnold says, close to 50-50.
Okay, I have one.
Arnold, yeah, I was just going to say, you might perhaps wish to invite our colleagues here to the conference tomorrow being opened by the former president.
We will talk afterwards about tomorrow's conference.
Yes,
But
tomorrow.
No, just finalize with questions and comments. I have one more comment. I don't know, possibly you have in Poland, but anyway, we have in our Institute of Physics vacuum chamber for space simulation. something like diameter 2 meters and some 4 meters long. With all equipment that you can reach this spectrum easily. Possibly you can use this opportunity for testing some.
We will consider it. We have our own, which is much smaller.
Yeah.
It's 1 meter in diameter, and let's say. Yeah, but I mean, anyway, you know, we calculated that we can put there a 50 kilogram satellite, not more. So yours is for like 200 or 300 kilogram satellite, which is already, you know, something that perhaps we should consider in the next stage. Yeah.
More questions? Colleagues? Some comments for discussion? More? Okay, thank you very much.
Thank you.